Welcome back. In our third video of gases, we will be discussing a couple of things at once. So we'll start here with Avogadro's law. And Avogadro's law pretty much states a simple fact. And the simple fact is that when the conditions of two gas samples, when they have the same temperature, pressure, and volume, so they have the same they have the same temperature, pressure, and volume, the same PTVs. Those two samples would always have to contain the same exact number of molecules, which can also be explained as the same number of moles. Those two words would be synonymous at this example. And so we can look at this picture, right? The picture explains it all. The temperature of all three balloons here is 273, so identical temperatures. The pressure of all three of these balloons is 101.3 kPa, so they would all have the same pressure. Now, in addition, what we're writing here is they have the same volume, 22.4 liters. And in this case, it doesn't make a difference what the gas is composed of. Doesn't matter at all what the gas is. We could have a monatomic, we could have a molecule, we could have a diatomic, all with different masses, all with different masses, all with different molecular shapes, different intermolecular forces. Everything about these samples of gas is completely different, but none of that makes a difference if the temperature, the pressure, and the volume are the same. All of them would have identical number of molecules. So in this picture, I tried to kind of highlight that for you and show that there are 1, 2, 3, 4, 5, 6, 7 molecules or 1 mole of argon, or 1, 2, 3, 5, 6, 7 molecules of carbon dioxide, or 1, 2, 3, 5, 6, 7 molecules of oxygen. Okay, so it's a very simple thing. Same temperature, same pressure, same volume, same number of molecules. And that's Avogadro's law. It only applies to gases. It doesn't apply to liquids or solids. And that pretty much sums it up. So we'll move on to the next concept, which is a little bit more, it's not really complicated as much as it is thought-provoking. So the way I like to teach this is I say, this is the kinetic molecular theory. Okay, the kinetic molecular theory consists of 4 postulates. 1, 2, 3, 4. And they're listed right here in a very similar way that the New York State Regents words them on the exam. Now, how I explain this to my students, and some of you are my students, is I call these the pretend behaviors of gas. Okay, they're the pretend behaviors of gas. We pretend that this is the situation in order for us to use gas calculations. Okay. So that's kind of like my little preface. These are not real situations, which you'll understand as we go through it. We just have to imagine or pretend that this is the conditions that gases behave in order for us to confidently make gas calculations. Number 1 says the particles themselves have no volume. Right? Now we know that, again, this is what I mean. We know every particle is made up of matter. And if it's made up of matter, it must have volume. But in our calculations, we have to pretend that this balloon, right, that is filled with oxygen gas, we pretend that that volume, whatever it may be, exists, and the molecules exist, but the actual atoms are kind of don't. And we pretend this for a very important reason. Obviously, the gas particles have a volume. And in a gas calculation, that would affect the volume being calculated. So we ignore that, or we just pretend, we ignore it, and we use all molecules, all particles, we treat them the same. We say that actual atoms themselves don't actually take up space. The second postulate says that regardless of what the molecule is made up of, there are no intermolecular forces. None. The molecules aren't attracted to one another. The molecules don't repel each other. They simply just exist in perpetuity without ever interacting. Now we know that this is not true. Obviously, if you have gas molecules that have strong intermolecular forces, they're going to pull on each other. And that would change the volume that we've calculated to be a smaller number. And obviously, if they repelled each other, it would make the volume get larger. So we ignore the intermolecular forces. We pretend that they don't exist so that we can use these gas calculations on all gases. The third one talks about the collisions. Right? So in a balloon, particles are always colliding. And when they do that, they lose energy. There's friction, there's heat. There is a transfer and a loss of energy in real life. But for the sake of this unit for New York State, and according to the kinetic molecular theory, we say that whenever particles collide, they don't lose any energy in total. So they can lose energy. Let's say you got, I'll just throw some easy numbers out here. 50 joules of energy moving through this particle. That's a lot, I understand that. And then you have another 50 joules of energy moving through this particle. When they collide, what can happen is they could bounce off of each other and travel again with 50 joules of energy, or one can gain all of the energy while one loses all of the energy. The point is, no energy actually gets lost. It can be transferred, but in a total collision, the same amount of energy the particles started with would be the same amount they end with. The reason we do this is it would affect the temperature readings. And again, we're trying to have a level playing field for all particles regardless. The last one just makes a statement. It's pretty simple. Particles, the way that they travel, constant, random, straight line motions. Something like that. And it just helps us predict the behavior that a gas molecule would have. Okay? So those are the four postulates. The best thing to do is to kind of just try and memorize the phrasings if you can't really understand the reasoning behind it. Okay, it's four things. It's not too much to kind of drill into your head, but those are the four. Now, with that said, we're going to just quickly talk about an ideal gas. So an ideal gas is one that follows the kinetic molecular theory most closely. Meaning an ideal gas pretty much has no volume, pretty much has no intermolecular forces, will have collisions that don't lose energy, will have particles traveling. in a constant random straight line motion. That would be an ideal gas, because those are the four conditions that make an ideal setting for gas calculations. So the ideal gases, that the two molecules that are most closely behaving like an ideal gas are hydrogen, H2, and helium. Okay, those two on their own will already behave as close to the KMT as possible. And that's good because it helps us with our calculations being more accurate. However, we can make any gas, behave more like an ideal gas. And to do that, we have to just have high temperatures and low pressures. The two things that does, that helps in this situation, is that high temperatures would make the molecules move really fast. And if the molecules are moving really fast, they're going to have less intermolecular forces on one another. They're just not going to have an opportunity to interact the faster that they move. The low pressure would essentially increase the volume and give the molecules more space to reside. And what that does is it decreases the ratio of the molecule size to the size of the gas. Right, so this dot taking up that much space is much more of a significant volume than if I had a dot, the same dot, in a much larger volume. Now this dot is what we would call much more negligible. It doesn't actually consume much of the space. And so that goes back to what we were talking about with the kinetic molecular theory, right? Gas molecules have a much more negligible volume if the volume that they are occupying is much larger. Okay, so that's the reason why. And the truth is, in reality, gases aren't ideal. They're not. They attract each other, they repel each other. The particles have volume. Really large molecules of gas have very large volumes. And so we have to pretend, or we have to set the conditions, high temperature, low pressure, to get gases to behave the way we want them to be. All right, I hope you enjoyed the video about Avogadro's law, kinetic molecular theory, and ideal gases, and I hope you stay tuned for the final video of this unit. Thank you very much. Like and subscribe.